6, 5, 4, 3, 2, 1, 0. We have commit and we have liftoff at 2:13. 7.5 pounds of thrust, and it has cleared the tower.
Prepare yourself for a world of science.
What is going on, everybody? It's time for the Science Nights, just after 10 o'clock on Saturday, and we are here assembled with Dr. Thomas Shiller and Dr. Sean Graham. Dr. Anirban Bhattacharjee out doing research. He's on the field, can't make it, but he will be back soon, so be sure and stay tuned in. Now, we are going to talk a little bit about the birth of the Rockies. Now, right. I know that I like to go to Colorado to get really, really high up in the mountains.
Elevation,
yes.
Yeah.
And that is the only reason why I go to Colorado.
Definitely.
But no, to be real, like, you know, our family takes... we take vacations to Colorado on a regular basis.
It's a
beautiful.
It's kind of scenic, just a little bit.
Yeah,
sure. I mean, you go through New Mexico and kind of take the little trip there. But I never really even thought about how those beautiful formations happened. Mm-hmm. You know, and
the birth of the Rockies.
You're gonna tell us a little about how it all happened,
yeah,
right?
How the Rockies.
So how long ago? I mean, was it like? Millions, billions? How many years?
So it all started when a mommy mountain and a daddy mountain loved each other very much, about 300 million years ago. So the story of the Rockies goes back a long, long time ago. It wasn't just attributed to a single event. The Rockies kind of preserve a really rich geologic history that kind of goes back even before 300 million years. But the first kind of event that rooted the Rockies happened around anywhere from 200 to 300 million years ago. And in either case, when the Rocky Mountains formed, both the ancestral Rockies, as we call them, the first event that shaped the earliest Rocky Mountains, and the event that occurred much later that formed the Rockies that we have today, we use this term orogeny, or an orogenic event.
Oh, okay. Orogeny equals origin. Somewhat?
I think it's the same root as erogenous, right?
Okay.
And so if you think of an erogenous zone, like climax, orgasm, peak, I think that's...
a pinnacle.
Yeah, I think it has to do with that.
Yeah.
So it's orogeny and erogenous do have the same root, but think about it as a peak.
Yeah,
and we're talking about the origin of these peaks.
And in simple terms, it's a mountain building event.
Yeah.
Yeah.
And in the case of the Rockies, we're talking about the main building event is the Laramide orogeny. And the Laramide occurred, some folks say it happened 70 million years ago. Some people say 80 million. There are even other people who say it started 90 million years ago.
And that would be the more recent mountain building episode?
Exactly.
You mentioned one that was way earlier than I'd ever thought of for the Rockies, 200 million years.
Yeah,
and obviously the rocks themselves are really old.
Yeah.
But then there was an early period. I'd never heard of. I'm very excited to hear about this.
Yeah, so when we look at North American mountain ranges, specifically the Rocky Mountains, the Appalachians, in most cases, they're related to multiple orogenic events, multiple mountain building events. And we know that that's happened because all of these geologic features related to mountain building are kind of superimposed upon each other, and we have sort of a chronology. And when it comes to the earliest event that shaped the Rockies, we have all of these rocks that were folded and faulted and then eroded down, and then subsequently when the most recent orogenic event related to the Rocky Mountains happened, the one that actually pushed up the mountains that we see today, we find these older rocks that rooted the original Rocky Mountain range, folded and faulted even more and thrusted up, so that we have a really complicated story in terms of the structure of the Rocky Mountains that's basically telling us that there have been at least 2 phases of orogeny that have taken place.
And that early one, are there any remnants of the original mountain range from 200 million years ago that are actually mountains, or is it just
not physiographic?
eroded?
Yeah, it's just the core of the mountain.
I see. Yeah.
So this kind of takes us to the general concept of mountain building, and one of the reasons we know how it takes place, the mechanism behind it, at least when it comes to the Rocky Mountains, is it all has to do with the geology, with the stratigraphy that we find within the mountains. Basically, the stacking of the rocks and how they've subsequently been deformed or faulted. So when it comes to the Rocky Mountains, we'll talk about this in kind of a broader scale first. An event that's related to oceanic to continental convergence. Now, we've had an episode about plate tectonics before, and we've done kind of the introduction of plate tectonics, but for the people who didn't hear that episode, I'll do kind of a quick review. So, on the surface of the Earth, we have what we call the tectonic plates, and they move and they interact with each other. These tectonic plates range in size, and they vary in how they interact with adjacent plates. But in any case, the tectonic plates are made up of what's called the lithosphere, which is this rigid upper part of the Earth that comprises both the upper mantle, okay, the second most voluminous layer of the Earth, and the crust. So these rigid plates move about on top of a layer that's called the asthenosphere that behaves a lot like a liquid. It's not entirely liquid, but it allows for the plates to move around. So because the plates are moving, they're being driven by heat that's circulating within the mantle, convection, just like what your oven does, pushing heat upward and having cold materials sink. This is what drives plate tectonics. Now, as I said before, the plates are constantly moving at different rates, and they're interacting with each other. They can do a number of different things when they interact with each other. You can have 2 plates made up of mostly continental crust, in other words, thicker, less dense crust, and they can collide with each other. And they form some really dramatic mountains like we see in the Himalaya. That's a good example of that.
When India smashed into Asia, right?
Correct, yeah. So drove up these huge
continents
mountains.
collided.
That's another orogenic event, another mountain building event that's slightly different than the laramide orogeny, which we're going to talk about here shortly. You can have 2 oceanic plates that collide, and one of those plates will typically subduct beneath the other. And what that forms are volcanic island arcs, okay, like we see in Indonesia, where the subducting plate drives volcanism above the overlying plate. That's not what happened with the laramide either. What we see with the laramide is 2 plates colliding, one of them oceanic, one of them continental. The oceanic crust is made up of much more dense material, so it tends to sink or subduct, as we say.
It's also lower down, right? It would automatically be under the ocean. I would feel like it would have a tendency. It'd be really. I wonder if that's ever happened where you'd have oceanic crust slide over a continent.
No.
It just the tendency would be for it to go under the continent.
It's much more dense, and like you said, it's slightly lower, and it's not as thick.
Yeah.
So imagine you have continental crust, which averages around 70 kilometers thick. The oceanic crust is averaging maybe 10 or 15.
Yeah.
So it's only a small percentage of the thickness. And so in the case of the laramide orogeny, we had what was called the Farallon plate, which is this enormous oceanic plate. Extended all the way down to South America. And in the later part of the Cretaceous, around 80 million years ago, it starts to sink beneath the North American plate. Now, this might seem like a long time ago, 80 million years. In geologic terms, it's really not that long ago. So we still have remnants of the Farallon plate today.
That's what I was going to ask you. That was my first point of confusion. Where is the modern Farallon plate? Is it still out there?
So most of the Farallon plate is way deep beneath our feet. It's been subducted already.
Yeah.
But we split up the modern Farallon, at least where it's exposed in the oceanic crust, into a number of different smaller plates. We've got the Cocos Plate, the Gorda Plate, the Explorer Plate,
Wanda Fuca
Plate.
Okay, cool.
So people are probably familiar with
That's
that.
one I've heard of. And,
Yeah, because that has to do with the San Andreas fault system.
Yeah.
So the Farallon Plate's still around, but it's in small little pieces. The Nazca Plate down in South America, the
and all of
subducting
those
plate.
are tiny little fragments of this former big plate that are just kind of glued on to the western margin of North and South America now.
Correct. Yeah.
Yeah, and
they're still actively
and doing weird things.
Yeah, they're still moving, and they're driving basically the tectonism that's going on, and the volcanism that's going on in western, specifically northwestern North America. But these all relate to this bigger plate that's subducted beneath the North American plate.
And the
millions
rest of
years
it's
ago.
still it's up underneath like the Rockies and the Andes
Yeah.
and the
And we know
Sierra
that
Madres.
because we can map that stuff in the subsurface. We have seismic tomography. If Anirban were here, he could expand on that. But basically, we understand how seismic waves move through material, and we can effectively map bodies of rock in the subsurface, including the bulk of the Farallon Plate that's beneath us. Right?
Wow. So yeah, the density of that stuff would be slightly different. So you could, I know one little I know about how how seismic, waves can be used to kind of figure out what's underneath the surface. You just kind of you would bombard the crust with seismic.
Yeah.
Right.
Sound waves or vibrations.
Actually, I don't know how that's done though. Like physically, how's that done? I know we're getting off topic a little bit, but
No, this is good.
is there a machine that does that, or
Well, in the very shallow part of the crust, you can do it with a machine. People who live in the oil patch up in Midland, Odessa, may have seen some of these seismic stations. They have these big trucks that can generate seismic waves. They basically
Wow.
thump the ground.
yeah,
But that's like within just a few.
it doesn't go.
Few
I
meters.
wouldn't imagine that would go very far.
So the seismic data that geophysicists are getting for something like doing seismic tomography, that's coming from earthquakes.
Yeah.
Because earthquakes, large-scale earthquakes, generate enough energy that they can pass seismic waves all the way through the interior of the Earth.
Yeah.
So geophysicists, seismologists, they have stations all over the surface that can collect those seismic data and process them and essentially form really cool three-dimensional maps. I would recommend people go look at seismic tomographic images because they're really neat. This is something we haven't been capable of doing until recently. So we're basically looking at something that we previously could not directly observe in an indirect fashion. And physics is doing that for us, but Dr. Bhattacharjee isn't here to talk about that.
So I can imagine this would be like if you were to take pieces of peanut brittle, right, and smash them up against each other. And if one side would slide under the other, you would get fragments of peanut brittle. And you might even be able to still kind of image that, a three-dimensional chunk of the old Farallon up underneath the Rockies.
100 kilometers.
That's incredible. I would love to see. That would be awesome to see.
Yeah. And you
Something
can
like
you can
that.
even image what's going on in the deeper part of the mantle.
Oh, wow.
And I think we talked about this. It's been a while since we talked about plate tectonics. But we've always had this kind of simplistic model of how heat exchanges within the mantle.
Yeah.
Heat rises and cold sinks. So the original idea was that there was this really large-scale convective pattern that occurs within the mantle. And it does. But that's not the only thing that happens. When a subducting plate, like we talked about, like an oceanic plate, dives within the Earth, it can do a couple of different things. It can, and we'll talk about how this relates to the laramide here shortly. It can continue to dive deep down within the mantle, and it can be partially melted. It can get all the way down to the core mantle boundary and basically be remelted and incorporated into the melt.
Completely disintegrate.
Yeah,
right?
it can sink to a certain depth, and it reaches a barrier, and it kind of moves horizontally.
Huh. Oh yeah, that kind of, if you can imagine that, imagine putting that peanut brittle right and it's sitting on some sort of kind of molten chocolate, right?
Yeah.
And so when it collides with another piece, it doesn't have to, especially if that molten chocolate's like bubbling in the top of a pot.
Yeah.
Right. Anything could happen. It could shift to the left or right. But from what I've read, right, the Rockies, did it shoot down and then buoy back up and cause a big
That's kind of the most popular hypothesis currently.
Because the weird thing about the Rockies, right, is that they're so far interior.
Yeah.
Yeah, because like the Sierra Nevada and the Coast Ranges, those would be in about the position of a normal plate boundary interaction.
Yeah.
Like the Andes are right along the coast, so there's nothing really
Yeah.
hard to explain there. The Himalayas, it's a suture between two continents, so there's no mystery there. But the Rockies are way interior.
They're
Yeah.
1,000. The front range of the front range of the Rockies are about 1,000 miles from the margin of the
And
continent.
that's where, is the current model? So you were listing a couple of options. Is there an option that explains that option D?
There is, yeah, and it's really a unique scenario, and it's something that scientists have been aware of for a little while, but just kind of the intricacies of it aren't entirely understood because we don't really have any other examples of this. Now, the general model is that instead of having this kind of high angle subduction, which is the textbook model of a convergent boundary, where the subducting plate is at like 45 degrees and it's diving at a steep angle down into the mantle. This would explain why you have volcanoes and mountains that are forming right along the margin of a continent. We see this in South America with the Nazca Plate diving beneath South America and forming the Andes, basically. But, like you said, Dr. Graham, what we have in the case of North America are the Rocky Mountains, which are 1,000 miles from the continental margin. So we have to come up with a scenario that explains that. And the scenario we talk about is shallow subduction, where the subducting plate, rather than diving at like 45-degree angles, is at a much higher angle. So 10 to 30 degrees, something like that. So that as the laramide orogeny is taking place, the subducting plate actually reaches this portion of North America.
Oh yeah, okay.
And now, generally speaking, when talking about, do we have enough time for this,
Yeah.
Connor? Talking about orogenies and orogenic events, we associate those things with a couple of different geologic features. One being volcanoes, and after the break we'll talk about how that happens, and the other being big folds and faults. So rock that's been deformed and it's been broken and faulted in some way. And that all has to do with this stress that's being applied to the rocks. In this case, compressive stress, so two forces moving in opposite directions. So just like if you took a sheet of paper and you crinkled it up, you applied compression to it, you'd form folds. If it were a rigid body, you'd form faults, so on and so forth. So this is what we associate with these mountain building events. If you go to the Himalaya, which is a pretty clear example of continental convergence, you see this. You see structural complexity as these rocks are being driven up through tectonic forces. In the case of the Rockies, we see that, but again, it's way far inland. So we have the Farallon Plate that's subducting beneath North America. The initial phases of that involve volcanism. So the plate is subducting at depth. That rock, that oceanic crust, starts to melt as it gets deeper within the earth. Temperature increases, so rock can actually melt. And that molten material is driven up through the crust. Mm-hmm. And in the case of the Rockies, specifically the Sierra Madre Occidental, along the western coast of Mexico, that starts driving volcanism to happen. So we have...
That's the first phase of the Laramide?
That's the first phase of the Laramide, and why we have these big remnants of volcanic peaks in western Mexico. So that's taking place way off to the west. Some scientists even suggest that this was starting 90 million years ago, so 10 million years before the 80 million year estimate. And that's related to actually finding particles or pieces of sediment related to those volcanic mountains in rocks further to the east. But that's kind of the first phase. It's driving volcanism. And at the same time, those volcanoes that are being driven up are also starting to become folded and faulted and deformed. So some of the complexity related to the Sierra Madre Occidental has to do with kind of polyphase geologic events happening.
All right, well, that's the first phase, and we're going to get to the second phase and maybe explain to everybody what the Sierra Madre are. For those of you guys who might not be familiar with stuff down south of the border, we're going to do that right after the break. Come on back and listen to Science Nights in the morning.
All right, everybody, we are back with the Science Nights, and Thomas Schiller's talking about the birth of the Rockies today. But what I want to know is the flora and fauna of the area before the Rocky Mountains even came to be. Can you describe or illustrate that?
So let me give you a setting here. We've talked about the Western Interior Seaway before. So imagine the North American continent doesn't look entirely different than it does today. The one big difference is there's a shallow seaway that's extending up from the Gulf of Mexico up through Canada. Mm-hmm. And obviously that's going to affect the flora and fauna adjacent to the Western Interior. So we're talking mainly, if you can think of like a tropical or a subtropical type habitat with dinosaurs.
Dinosaurs.
Yeah. So this is the time of the dinosaurs. We have the big long-necked dinosaurs running around, T-Rex, Triceratops, all the ones that were in your coloring book when you were a kid. But the Rockies aren't quite there yet.
Is that why the Rockies right now are so riverous?
How do you mean?
They have a lot of rivers. There's winding.
Well,
there's a lot of water.
Yeah, so that's related to them being mountains. When you have an elevated region, you have runoff of water, surface runoff of water, and you form rivers.
Okay.
Now that's an important thing, and we'll talk about that shortly, because when the Rockies started to form, it did have an effect on the overall physiography of North America at the time. We've talked about that when talking about Big Bend, so I'll bring it back to that later on. But it does have a huge effect. Mm-hmm. But kind of imagine your dinosaur book when you were a kid, where you have dinosaurs roaming around. It's tropical, subtropical type environment, but there aren't big, jagged peaks like we see.
No Dimetrodon.
No, they've been gone for a while.
Okay.
They're extinct, but it is really flat, except for this, ancestral Rockies that would have built up 100 million years before or so, and the Appalachians, which had formed a long time ago. North America was not very mountainous, so imagine a big flat area.
Yeah. Sure.
Which
like
is good
plains.
Imagine like the Amazon basin or something like that, where it's just super flat and it's low, and there's a lot. There would still be a lot of water because there's it's a tropical climate, so there's plenty of rainfall.
Yeah.
So it's a totally different, completely different than it is now.
Yeah, and the laramide orogeny starts to change those things.
Yes.
And the first phase of that involves the volcanism that's going on in Mexico.
And you said the Sierra Madre before the break. And some listeners might not be that familiar that the Rockies have kind of a twin range in Mexico that is also kind of a twin range. There's two sets of mountain ranges on either side of Mexico, on the kind of Gulf Coast and the Pacific Coast. The Sierra Madre Occidental.
Yep. To the
and
west.
The Sierra Madre Oriental. And it just means Sierra Madre West and Sierra Madre East. Mm-hmm. And in between that is this big kind of flat, plateau, where the Chihuahuan Desert is, more or less, because those mountains kind of pull all the moisture from those, the ocean basins, and the rain drops on either side of them, but then it pulls the moisture out, and so that in between the two mountain ranges is very dry, and that's kind of where we are.
Is that more or less how the Rio Grande is?
The Rio Grande runs straight through the northern tip of the Sierra Madre Oriental. Yeah.
Okay.
But the one that has at the beginning of the Rockies, the one I'm kind of interested in right now is this western one along the west coast of Mexico, which started it all off.
Yeah.
Right?
So, again, we have the Farallon plate subducting that's driving volcanism. It's driving deformation, folding and faulting of the overlying crust. And what we get are the earliest stages of a mountain range, the Sierra Madre Occidental. Now, as a sedimentary geologist, I study soft rocks. I have to kind of relate this to the evidence that we find in that record. So we have the mountains themselves that we can go and study. But in order to determine when this happens, we have to look at the record as a whole. Now, when a mountain range is driven up, when you drive up any amount of rock and expose it at the surface, you're basically driving, or you're providing more material for erosion, which leads to more sediment,
Right.
which is what I'm interested in. So when the Sierra Madre Occidental is driven up, we see this huge pulse of sediment moving to the east,
Sure.
which starts to fill in the basin, the western interior seaway that we just talked about.
Mm-hmm.
Out here in Big Bend, we see that happen in the rock record. All of a sudden, we find sedimentary rocks that are made up of pieces of that material off in the Sierra Madre. So we have a good constraint on when it begins, and we have sedimentary evidence of that. And in the meantime, dinosaurs.
So dinosaurs you're pulling out of the Big Bend are pulling out of sediments from the eroding Sierra Madre Occidental.
At least those
cool.
in the lower part of the Aguja Formation.
Yeah.
So the kind of the earliest dinosaurs that we find, and this basically leads to the initial phase of the western interior margin moving back to the Gulf of Mexico, the regression of the western interior seaway, because we have more sediment that's filling in the basin. Okay, so the next phase, since we're talking about the Sierra Madre, happens later as the Laramide progresses. So the plate that's being driven beneath North America is driven further and further within the continent, and it starts to push up mountains in the interior.
So it is kind of buoying up. It's like if you were to shove a life jacket under somebody, and it suddenly
Buoyant.
kind of
Yeah,
pops
right.
up. Yeah.
It's driving up the crust, and it's also driving volcanism.
And where's the first evidence that it starts pushing up like that? Like what range or what area?
So now we're getting closer to the Rockies,
The modern Rockies.
the modern
yeah.
Rockies.
Wow.
Yeah, so
So it's all progressing to what we see
yeah,
right
and
now.
the cool thing about it is, if you look at the research that's been done related to this, is there's this pattern that we would expect. We see structures and volcanoes associated with the Laramide moving geographically from the southwest to the northeast towards the front range of the Rockies. So it all makes sense, and there's a chronology to it. And we see the same thing down here, because we have basically the southern part of the Rockies exposed here in Texas.
Sure.
And then we have the Sierra Madre Oriental to the south of us.
Did the Oriental play into this? Are they part of the Laramide?
The Oriental is kind of the later, at least in the Cretaceous, the later phase of the Laramide orogeny.
Okay. So kind of they're more kind of paired with the actual Rockies themselves than the
Yeah.
Occidental.
Yeah, they're
The same time
a
period.
closer longitudinal line.
Yeah, okay.
Basically. But so going back to the Rockies, as the subducting Farallon plate is moving further and further within the interior of the continent, like you said, Sean, it's acting as a buoy. It's pushing up the overlying crust. So what is that crust? Well, we have millions and millions of years of geologic events that have been taking place in North America. So the crust is made up of really old metamorphic rock that you can see in the Grand Canyon. You can see
At
it
the bottom.
the bottom
basement,
of the
right?
Grand. Yeah. Then you can see it on the top of the Grand Tetons. So this basement rock that is kind of the core of the continent is being driven up beneath this new mountain range. And above that is younger sedimentary rock, going all the way back to the Paleozoic, all the way up through the earlier part of the Mesozoic. So a big stack of sediments on top of that. And it's all being pushed up, it's being eroded, and in some places there are volcanoes that are popping up within it. So making for a really complex story.
Yeah.
And the Colorado Plateau is like a big chunk of that original flat stuff that was there pushed up in whole, right?
Yeah. Just a big
It didn't
big
get
block
it didn't
of
come out in like some angular kind of direction where it could easily erode into like toothy mountains. It's just like it pushed it up as a giant chunk in situ, like all by itself. And then the river carved a big canyon
Yeah.
simultaneously.
Yeah, and that's why if you go to the Grand Canyon and you look across the spans of the canyon, you don't see really folded and contorted and faulted rocks. They're nice horizontal sedimentary rocks that were just kind of pushed up
Yeah.
in a rigid fashion, which
So-
is one of the incredible things about the Grand Canyon.
How many years does that take? Like, it would be rapid, like, versus any other mountain you'd
Relatively,
see, right?
Yeah.
The carving of the canyon, I think, was pretty rapid.
Right.
Yeah, it's always good to remember that the rocks of the canyon are ridiculously old.
Yeah,
The canyon
sure.
itself is not terribly old.
Yeah.
And because the Rockies themselves, geologically speaking, not
They're
terribly
relatively
old.
young, yeah.
Like they said, the youngest range, right? They always talk about the Grand Tetons. They're some of the most kind of stark-looking, really jagged-looking of the Rockies, and they're considered, I think, one of the youngest ones.
Yeah.
You get that kind of really jagged appearance in really young mountains, like
Yeah.
the Himalayas, parts of the
Oh,
Alps.
okay.
And the older mountains, like the Appalachians, they get worn down to nothing. So there's hardly anything left, since they're nice and like round hills.
Yeah,
Yeah.
and that's
Level
that's
and-
kind of one of my favorite exam questions that I give when talking about mountains in my introductory geology classes. How can you tell the difference between a really, really old mountain range compared to a young one? And
The erosion, right?
Yeah, the Himalayas are a great example because they're super tall and they haven't been eroded that much. They're really jagged. The Tetons that we have here in North America, relatively young. They're related to basin and range tectonism. So they're really jagged and steep and high in elevation. But like you were saying, the Appalachians are just kind of
Way
eroded
older,
down.
and there's hardly any of them.
Yeah, they would have
look
been
like-
an incredibly huge,
Yeah.
tall mountain range at one point.
It would have
but
been impressive to see them. You're looking at like an old worn teeth.
You're talking about, like, an event that happened over a span of how many years?
The
for the
Appalachians
For the Appalachians.
for the Appalachians,
supposed to be
well-
one that it's like the Permian Triassic collision between Africa.
yeah,
and
it would have
North
been several
America.
millions of years. But the
300.
Appalachians are also kind of a polyphase mountain range because
Oh, okay.
yeah, their root is older than the most recent orogenic event.
Huh. Okay.
But the Appalachians, like Sean was saying, is related to the collision of Laurentia and Gondwana and form this big smushed up sandwich in between the two major continents of the time.
Sure.
And subsequently they've been eroded down. Erosion and weathering can destroy anything, especially if you have millions of years to do it.
It's amazing
Right.
to think as these mountains are being built up, and if you camp out in front of the Grand Tetons and see if you can see them changing. You're not. It happens over millions of years, but it's amazing to think that they're being pushed up, or at least the valley is being pushed down at this rate where erosion can make it to where they're only going to get 13,000 feet. They're not going to get much taller because erosion's bringing them down as fast as they can be pushed up. But okay, so you've done a great job explaining. I'm really starting to picture how this would have happened with the Sierra Madres, the volcanism, and then the central part of the Rockies, the Colorado Plateau. All that's happening now. Here's a huge curveball for me. Part of the Laramide orogeny is this other weird terrain west of it. Between the Sierra Nevada and the Rockies, there's a bunch of mountains, little bitty mountains,
Tiny ones.
Yeah, little bitty islands, right? The Great Basin, the Basin and Range, and honestly, that's kind of that we're in a basin and range topography where we are here in West Texas. It extends from the Great Basin, Nevada, Utah, down into Mexico, where you have these tiny little ranges, like little ships in the sea, and a nearby basin right next to them. And right now they're all dry. They were lakes, in the Pleistocene, the Ice Age, but now they're all dry. So it's a desert area. And that's a part where I thought I understood how that terrain came about. But it's a little, please explain it to me. At what time did this terrain start to become present?
Again, there are two components to that story. Okay. If we go back to when the Laramide is happening, in addition to driving up mountains, and we see this out here in West Texas, you also form valleys or basins. Mm-hmm. Now, typically when we talk about basins, we talk about ocean basins or gulfs. We think marine basins. But when mountains form, they form inland basins or intermontane basins, which are low areas in between uplifted mountains. So all of these smaller basins that basically parallel the Rocky Mountain corridor up through North America initially are related to that compression of the laramide. And I can give a great example of one right here in West Texas. We're still in the late Cretaceous, the time of the dinosaurs, and the laramide orogeny has progressed to an extent that it's starting to directly affect this area and the Rocky Mountains to the north. So we have deformation and volcanism taking place related to that. The big kind of region that's defined by that in this part of the country is the Chihuahuan tectonic belt, which forms the Sierra Madre Oriental,
Right.
where we have old sedimentary rocks that are pushed up, they're
Lifted up,
uplifted,
yeah.
and they're deformed by the laramide orogeny. We don't necessarily associate all of that with really intense volcanism. We know that it was happening, but mostly what we're talking about is deformation.
Yeah.
So big
And
folds and
that's
faults.
south of where we are, right? There's
Yeah.
huge lines of mountains in like Coahuila, Nuevo Leon, where there's these just gigantic long ridges, and you can look at them and see they're limestone, and there's just like they've just been pushed up as a big,
Right.
gigantic,
Yeah,
like
completely
yeah,
vertical.
yeah.
Like,
Now, the cool thing about how this relates to Big Bend is because when you drive into the national park, you're basically driving into a basin.
Mm-hmm.
You go down in elevation as you approach the Jesus Mountains in the center of the park, and of course you go up in elevation when you go up in the mountains. But generally speaking, you're driving into a big basin. The current configuration relates to another tectonic event that took place after the laramide, basin and range tectonism, which relates to the basins you were talking about too. But during the later stages of the laramide orogeny, in the late part of the Cretaceous, there's still dinosaurs, but we've changed the environment really dramatically. The western interior has migrated back to the Gulf of Mexico, so we are within the upland region of the continent. We're in the interior of the continent, and the laramide now is driving up older sedimentary rocks, forming basically mountains or big folds in this region, like the ones we see to the south of us. Here in Big Bend, or in Big Bend National Park region, there were two big folds that were driven up. The rocks were folded up and pushed up, basically in the same position that the modern Del Carmen fault that we see on the east side of the park and the Terralingual fault on the west side of the park. But rather than being faults, they were just big folds. And in between was a basin. And like you were mentioning, Conley, about rivers, that basin would have been a depot center, as we call it,
right.
for
Right.
runoff, for rivers that were forming, flowing down these slopes. So here's a basin that was formed inland, related to the laramide orogeny. It has to do with paleontology, too. Like I said, it changes the landscape, but it also kind of drives the deposition that preserves some of the later dinosaurs that we have in the fossil record, including those that are found up north in other areas along the front range of the Rockies.
Huh.
So that was how the laramide relates to our region here. If we move forward to kind of add some complexity to it, this doesn't necessarily directly have to do with the laramide, although they are connected. Starting about 17 million years ago, not too long ago geologically speaking, we changed the stress that's occurring within the North American continent from compressive stress to tensional stress.
It's a rebound.
Yeah.
It's a rebound, basically.
Is that
yeah.
what it is? Because I thought the basin and range was it's a rift. It's the beginning of a rift,
Yeah,
right?
exactly.
So you have the Sierra Nevada to the west and the Rockies, and in between that's the basin and range, and the basin and range is supposed to be where there's actually the plates moving apart again, and so you've got
Right.
this slipping of little. It's like if you were to put a bunch of sand between your
just-
fingers,
yeah, it
and it
slips
starts to
through.
slip through. That's what's going on.
Yep.
And that's what. So after the collision, we have a rebound.
Basically,
Is that
yeah.
what it is?
And
How
now
cool.
the intricacies of that are a point of debate amongst geologists.
I imagine. Yeah.
I don't even understand it entirely because I'm not a structural geologist, but it does relate to the subduction of the Farallon Plate because the activity that's supposedly driving basin and range is related to the San Andreas. At least that's one of the more
That's what I was-
popular
yeah,
hypotheses.
my last curveball was going to be, because all this compression, it's building the Rockies, building the Madres, but then you get these weird things that are related to lack of pressure or movement away, like the San Andreas.
That's right.
And so that's the part that, these two curveballs, I think we're going to be able to pull it all together after the break. First, we know how the basin and range forms, and now the last thing is, how do you get that crazy shearing to the northwest that is the San Andreas? And I guess we'll cover that when we get back. We're Science Nights in the Morning.
All right, we're back. This is Tom Shiller with the Science Nights. Today we're talking about a really interesting topic, the laramide orogeny and how mountains are built, especially those here in North America. And we're trying to kind of simplify things, trying to simplify a story that's really not that simple. So I hope I've done an okay job of doing that so far. But the last chapter of the story has to do with what happens after the Rocky Mountains are formed. We talked about kind of the complex history of the Rocky Mountains, how they relate to this laramide orogeny, the mountain building event. So what happens afterwards? We know that not every mountain in the western part of North America relates directly to the laramide orogeny or to the Rocky Mountains, although geographically speaking, they're all kind of linked together because they follow the same kind of mountain chain, basically, that extends all the way down to Mexico.
And we
Canada.
haven't even talked about the Sierra Nevada. We don't have time. Those of you guys who are listening in California, sorry, we're just not into it. So we're going to concentrate on the central.
Maybe
part.
another show.
Maybe another show. But yeah, so we got those.
Join our Patreon.
Yeah,
we'll talk about it.
If you donate enough, we'll talk about whatever you want.
Yeah. Maybe if you donate some Sierra Nevadas, we'll talk about Sierra Nevada.
Go for it.
But yeah, we got all these small isolated mountain ranges that are part of kind of a totally different, pattern. The Rockies are from the crust diving under at a shallow angle, popping back up, forming the Sierra Oriental and the Rockies themselves. But all those tiny little isolated mountains, a lot of the ones we have in West Texas, are part of that basin and range terrain, which is more from the plates eventually starting to slide away from each other again. So honestly, I don't even think they should be considered part of the same mountain.
No, and I think, like I said, it all has to do with geography, with maps. They link with the Rockies, so people consider them part of the Rockies.
And from a biology standpoint, they have a lot in common, but they're more like little islands that are off of a kind of a main
sapperlings.
Yeah, they're tiny,
little
archipelago out there.
Yeah. Okay, so the last chapter of the story here, after the laramide has finished up, like you kind of described it, Sean, things have to rebound because we've taken the rigid crust, the North American continent, and for millions of years we've applied compressive stress to it. We've got forces in either direction that are so intense that they're driving up enormous mountains. So when that's relieved, at least in part, things have to kind of rebound. And one of the hypotheses related to the basin and range, which occurred from starting around 17 million years ago, arguably is still happening today, is that these smaller mountains that are much younger, related to basin and range, formed from basically the rebound of the crust, driving tensional stress rather than compressive stress. So to kind of describe what I mean there is, when you take a rigid body of rock and you apply compression to it, this is where you push things up and you form folds and faults. When you do the opposite, you pull it away, you form mainly faults that start dropping down blocks, which we call grabens. We call these pushed up areas related to this Horsts, not horse, but Horst, and grabens.
Those are great names, Horst and Graben. I'm guessing a German got in there and named some things while we weren't looking.
Yeah, there's a lot of German terms in geology, and that's a couple of them. But this is what we see kind of paralleling the Rocky Mountains up through North America. The Grand Tetons are a good example of that, where the Tetons themselves are a big Horst that's been driven up. And if you drive through the other part of Wyoming, the eastern part of Wyoming, it's in a big graben.
Yeah.
You basically go from these beautiful scenic mountains to just flat plains. So that's the Horst and graben. The kind of modern clues that we see associated with that are faults that are going on along the western margin of the continent related to San Andreas Fault.
Yeah, so at some point this rebound led to this weird It's called is that a shear fault? What do you call those? A slip
It's
fault.
it's a transform plate boundary,
Okay,
or a strike slip fault.
that's the one I was
Yeah.
looking for.
Transform refers to the
strike slip.
Yeah,
refers
strike
to the
slip.
plate boundary.
That's the one I
Strike
was thinking
slip
of.
refers to the motion.
And
Yeah.
it's this, after all of this, there's this weird northwestern movement.
Yeah.
Where, California is shifting towards the northwest. Baja California,
Yep.
parts of Baja California were formerly attached to Mexico and sheared off to the northwest.
Yep.
And that's crazy. And how do you account for that after this crazy northeastern ramming of the Farallon plate into North America?
That's where the debate comes in, and it all has to do with the mechanism behind it. Because you could give a simple story like what I said, where the crust is rebounding, but then how do you explain the change in motion?
Yeah.
Why do we have a shift from, or I should say, the kind of the change in the orientation of the stress?
Does it check out for like pool players, billiards? Can you get an angle like that if you were to shoot your 8-ball at a northeastern angle?
If
Will
you
it?
put a little English on it, I guess.
I'm guessing. I guess it could, right?
Yeah. Yeah, so physically it makes sense, and the thing is the mechanism behind it. Because, like I said, the simple way of putting it is this rebound. But to put it in more detailed geologic terms, when something like this happens and how the crust reacts to that is really kind of complex.
Mm-hmm.
Now, we have this concept of isostasy. It's a kind of a mouthful there. But you have to imagine the crust as being this kind of buoyant body of rock. So it can float, it can rise up on the layer that it's moving about on, and it can sink when it becomes thinner. And one of the models doesn't necessarily explain basin and range, but related to rifting and how a compressive stress field can be transformed into a tensional field, is you have the crust that's being basically pushed like an accordion and thrusting up all these mountains, basically thickening the crust, driving the lower part of the crust deeper within the earth, and you have big chunks of it that are cleaved off and incorporated back into the mantle. And that drives magmatism that forces magma up beneath the crust.
Dipiers and
Yeah, even on
everything.
a larger scale.
yeah.
And that the force of the magma rising up drives the crust apart, leading to tensional stress.
Right.
And this is kind of what's happening in the East African rift. Although it's more localized, it's a
Yeah, the East African rift is so much kind of simpler, because you look at the Red Sea, and it looks like it's Saudi Arabia has pulled off of Africa, and then you just look at the Rift Lakes and all of those deep areas of East Africa. It just looks like East Africa wants to leave Africa.
and there are volcanoes too.
Yeah, and there's the lowest point on the continent is at the bottom of this rift, and it's like, okay, but the big rift we got, we've got this big area of the western part of the continent that isn't particularly low, right, where the basin and range is. And then we've got what they call the New Mexico Rift, which the headwaters of the Rio Grande drive through. And then you've got, the San Andreas, where that's kind of obvious too. You can kind of imagine Baja California, shifting towards the northwest, and eventually California will do the same thing and be on its merry way towards Alaska.
Yeah. And you bring up a good point, and I'm going to kind of bring this back around to our local geology, is the direction of which this is happening. The San Andreas kind of has this northwest trend to it. And where this adds some complication to geology here in Big Bend is the structures that are oftentimes related to basin and range have the same kind of orientation as those related to laramide. So to add to the complexity, we have laramide structures that are older, that are cut by basin and range structures.
Uh-oh.
So it adds some complexity to the.
Here we go.
Well, no, I could kind of see how you could have push and tug and pull and part, and then release going on earlier.
Yeah, and
right?
here's the best
Yeah.
example that you can see today if you're driving in the national park. We talked about earlier in the story where we had two big folds that formed a basin in what's now Big Bend National Park. It's still a basin today, but it's not bound by two folds. It's bound by two faults, two big faults. Especially if you look at the Del Carmens off to the east, big fault scarp, a
Oh, yeah.
big
Oh, yeah.
exposure of the actual fault plane. The Terlingua Fault, that's on the west side of the park through which Santa Elena Canyon cuts. That's the opposite one, and they both mirror those two big Laramide age folds that bound the original, what's called the Tornillo Basin.
Yeah.
So you're
there's-
basically
there's a weak place for that fault
yeah,
to develop.
the faults
Yeah.
just cut through there. It was a good point for them to originate, and it forms the graben, the Big Bend graben that we have today. That's related to much more recent tectonic events of the basin and range. So it's a really cool story, and another reason why we're so fortunate to have Big Bend National Park here, because it tells several phases
Tells
of
the
that
whole
story.
story,
Yeah, and
yeah.
if you understand
Yeah.
what's going on, you can see all this complexity, and you can understand the story for yourself. So if you've never been down to Big Bend, I would hope that if you're an Alpine local, that you've at least been down there. But if you're a student or someone listening, or maybe you're listening to our podcast or listening to a stream online, if you haven't been to Big Bend, you have to go, because a big story like this, the Rocky Mountains, everyone knows about the Rocky Mountains, no matter where you live in North America. But here in the Big Bend, we have a pretty good record of that story as it happened down here, and we can relate that to this broader geologic story.
Yeah, that's great. And, for the listeners out there right now, if you have a question about anything that we've talked about in our past episodes, give us a call. 432-217-1983. 432-217-1983. Can you tell them about our Patreon?
Yeah, we have a Patreon page. We also have a YouTube page. We're just now starting to put up videos. You know, we started recording shows the beginning of the summer last year, so we have probably over 40 episodes now.
40
that
plus, yeah.
We're slowly putting them on YouTube, so if you've missed one of our episodes, you can check them out there. If you like listening to us, if you check out our YouTube page, swing by our Patreon page. You know, we have several tiers that you can donate to, the lowest one being $3 a month. That's not much. That's like half a Starbucks coffee or something. And we have some higher tiers where we can send you some cool swag too. We got
Flip-flops.
yeah, flip-flops, T-shirts, coffee cups, all sorts of cool things. So again, just to remind everyone out there, we're not making a profit from this. We have some kind of operational costs that we would like to be able to take care of. We have a very nice producer who is doing this basically gratis, and the radio station here in Alpine is letting us broadcast for free too. But we'd like to pay them some money, and we have equipment that we need to buy and all that. So if you enjoy listening to us, visit our Patreon. Just go in there and search for Science Nights in the Morning. We'll pop up. You can take a look at our tier system and donate.
Yeah, and definitely, if you want to keep yourself updated on everything that we're doing, just follow us on Facebook. Science Nights in the Morning.
Yeah, we
Just
like
type it
to
in.
we like to post scientific articles. So if you follow us on Facebook and you like your Facebook feed to have some science in it, any kind of interesting article we find and that we read, we're going to post it on there. And sometimes we comment on it too. So visit our Facebook, visit our Patreon, visit our YouTube. Like, subscribe. What else do people say?
Smash that like button.
Smash the like button.
Subscribe to our
Hit the bell.
Patreon.
Smash it.
Do it. That's what they say.
Yeah.
But you know what? Hey, this is Science Nights in the Morning, and you get to hear it free here on KVLF. You can hear it free on YouTube. And follow us and send a question our way sometime.
Yep. We'll see you next week.